you can really trace it back, and a lot of the authors that I cited to, back to Aristotle and the forming of ontologies, which is the study of being, but far more relevantly with Leibniz when he wrote his Principia Mathematica in the 1650s, which he came up with the idea of this Mathematica Universalis, which is this universal mathematical language that he was intending to use to scientifically record the way that we thought and interacted with the world.
Now, who's that again?
Leibniz. He was a philosopher and a mathematician. He's actually the other person that discovered calculus. Because there was Newton and then Leibniz. Leibniz was like this really popular, flamboyant professor, and he had all these like friends, and he was rich and affluent, and he was credited initially with discovering calculus, and he like showed up, he's like, oh, look at all the stuff I could do, and then they like brought that around to Newton, and Newton was like, yeah, let me go to like my tomb of books that I wrote on my shelf. Here's a few on calculus. And they're like, oh wow, this guy really knows what he's talking about. And so Newton is credited with it, but Leibniz was argued by some the initial, and certainly at the time the far more like recognized discoverer of calculus. But he also came with this guy Mathematica Universalis, and what's really amazing to me is that in the 1650s, his plan for this language was for it to be executed on computational devices. So he essentially like predicted artificial intelligence in the 1650s and began starting to write it. And then if you come to Bertrand Russell, who was actually Wittgenstein's teacher, which is really neat, we'll get to that a little bit later, but Bertrand Russell critiqued, Bertrand Russell critiqued Leibniz's Principia Mathematica, the book, in 1908, and in doing so created what's called type theory, which was also a huge response to Friese's naive set theory. And that was, it's a continuation of ontology and the shaping. It's talking about the way that we interact with the world and the way we understand the world and the systems and the schemas and the ways that we use to do that. And sets were one explanation. So there's a set of all apples, a set of all oranges, there's a set of all people with red hair, there's a set of all people with red hair who are dead. Like any set is basically posited forward, and it's brought into being in a sense. But there's a lot of issues with that, and Russell sort of brought a lot of this to the forefront, and the main response, one of this thing called Russell's paradox, which I won't get into, but it's the idea of this hierarchical ordering system, and that really changed a lot, and it really is effective and influential on computing sciences and even modern day programming languages. They all operate off of something called object-oriented programming principles, which is essentially just a hierarchical ordering of class types within a program structure, which is very much influenced very directly. They even have there's so many types of type theory now, ironically enough. But
types of type
theory. Which is really neat. And so that sort of coming of age in the early 1900s really started to found computational sciences and developments of programming languages through these formal logical derivations in these systems that we're doing. Even the syntax is highly prevalent when you get into digital circuits and stuff today, the same exact syntax. We even use truth tables, except they're zeros and ones instead of T's and F's. But so as we move forward, which is really cool, we get into so the 1940s and 50s, we start to have this really big turning point with Alan Turing, who is one of the most interesting people in history without a doubt.
Turing is the turning point.
Yeah, Turing is the turning point. But he was brilliant. He was actually the person who cracked the Nazi code that helped end World War II. Because initially when Germany invaded Poland, one of the key things that helped us win the war is Poland actually captured one of their translation devices. It's this big machine they used to encode their messages, their war messages. They captured that, and they had to actually break it. And Turing was the person who not only broke that and saved like so many lives. They used that on D-Day to actually send false messages, so they thought they were like storming the beach miles and miles down from where they actually did. And it was one of the reasons the invasion into continental Europe was actually successful. And so not only did he help win World War II, but he founded, and he's credited as the father of modern computer science. And he was eventually put to death because he was also a gay man. So all around, pretty influential, crazy character. But amidst all of that, he also posited what's called strong artificial intelligence. So weak artificial intelligence is demonstrated by like your phones and even like that toaster. Like it's pre-written, it follows a script, it demonstrates aspects of intelligence, the ability to use information and data, even apply that in an applicable way. But strong artificial intelligence takes that a step further, and it basically posits the idea that a computer system running the correct program is in itself a mind. Not like a mind, not akin to a mind, but a mind. And that's really revolutionary. And he's credited sort of as the birth of this study of artificial intelligence, but it also resulted in this progression of this idealism called computationalism. And computationalism takes his position and basically exacerbates it. And it creates, as computation essentialism, it follows basically along this metaphor that the wet work of our brain is akin to the hardware of a computer, and the program running on a computer is akin to our mind. And in this way, it falls along Cartesian dualism, or in what some authors refer to as the rationalistic tradition. But this idea of Cartesian dualism, that we have a mind that is distinct from our body, this body is this earthly thing, and this mind is entirely different, and yet they are some way related, that was really popular within philosophy up until quite a bit before this point, actually, within the computational development. But computationalism nevertheless ran rampant. It was this huge idea that really took hold within computational sciences and artificial intelligence up until about exactly 1980, when Searle released his paper, Minds, Brains, and Programs, which he posited the Chinese room thought experiment. But essentially, he came up with the conclusion, and the very apt one, that syntax does not beget semantics. And so at this point, when we're encoding and telling these computers to do things, they're just following a set of instructions. Right. And they're decoding things, and they're acting this way, and it's representative of weak artificial intelligence. But strong artificial intelligence does not seem to be